Hello, welcome to another exciting chapter of Introduction to Business Finance. In this chapter, we're going to be returning to our thinking about risk, and we're going to introduce a little bit of probability and statistics to be able to model risk in some better ways, some more robust ways. So with that said, let's jump right in. So far, we have considered risk, right? We talked about this in chapter 10 in particular, and we said in general, we've got to consider our risks, including risk-free risk and an increment for market risk and project-specific risk and duration risk. We have to consider these in our risk models somehow in either our cash flows or our discount rates, which usually, and for the rest of the term, we'll be using some sort of opportunity cost of capital discount rate. And we've been using point estimates for both of these, for our future cash flows and our discount rates. Some of the problems with this are that our opportunity cost of capitals and our future cash flows are both random variables. And as I just pointed out, we've been using their expected values without thinking about their distributions, about their probability distributions. So, for example, if we had a situation where we were looking at stupid manager or project-specific risk, we would say something like we felt there was a 90% probability that a promised cash flow in 2 years was going to be 100, but in our view, there was a 10% probability that the management would screw up, and we would get, in this case, nothing. So when in a case like this, we would estimate as a single point estimate our cash flow 2 as 90% times 100 plus 10% times 0, and that's equal to, of course, 90. And that allowed us to say something like, over the long haul, if we do a lot of projects just like this one, we expect on average that cash flow 2 would be $90. And what we haven't addressed in this model is something like what happens in this case, in this particular case, if the project manager screws up, and what is the probability of this screw up for this particular case. We've just gone ahead and used the $90. So now we're going to use probability and statistics to do better with our risk models. And what we'll be doing is we'll be looking at the probability distributions that are behind the expected values that we've computed previously. So for the above example, if we consider the entire distribution that got us to that $90, we'd say that cash flow 2 is estimated to follow a Bernoulli distribution. Bernoulli distribution is just a yes-no distribution, and it's distributed as probability of 90% that we get 100, probability of 10% that we get 0, and that gives us our expected value of 90. So we're going to be looking at everything, not just the expected value, but all of the cases that go into making that up. And this allows us to say more to our clients or our bosses if we're working for a CFO or a CEO. So we can say better things and more things. Like, for example, our best guess is that on average, our cash flow 2 for these types of projects is 90. That's what we've said before, but we can add to that. This is based on our view that 90% of these projects will pay the promised cash flow of 100, but 1 in 10 will flame out, resulting in a cash flow 2 of 0. So we're saying more here, so we're able to do a bit better. And this now explicitly captures for us the fact that those risky future cash flows may not happen in full or at all. So this way that we did this was twofold. We included our point statistic for reward, and that's our expected value of cash flow 2. And now we've added to that our spread of the probability distribution that got us the expected value for risk. So that's what gave us our worst outcome of 0 with 10% probability, best outcome of 100 with 90% probability. So we're just adding this understanding and analysis of probability distributions to our risk models. So let's look at an example here taken from the time frame March 2020 timeframe during the middle of this coronavirus outbreak in the United States. So if we were considering buying several bonds, let's see if we can do a full high quality probabilistic analysis of these bonds. So let's say we're looking at a treasury bond and a bond of General Electric and a bond of United Airlines. Okay, so the promised cash flow for the treasury bond is 100, and the worst case, and this is our estimate, so we've done some work on this that would be given to you in this class. There's a lot of analysis behind this. So we, or our general manager, our CFO, does a lot of work on this and estimates in the worst case, the Treasury is going to default. Why is it going to default? Well, it just allocated $2 trillion for the US economy for various functions, and they're going to have to sell bonds to make that happen, and maybe they're going to have a problem selling their bonds, that sort of thing. And we do say, however, the United States Treasury is still considered the safest thing in the world. So even in an extraordinary crisis like this, there's about a 1% probability that the Treasury is going to run into trouble with this bond. So what I'd like to do here is to fill in the missing information. So the expected value for this guy is exactly what we've been doing before in chapter 10 and on the previous pages of this lecture. So for our expected value, we're going to have 99% times 100 plus 1% times 80. Okay, and we'll work that out. And what do we get here? We get 99.8. So that's good. And now for GE is in a slightly different position. GE is a case of a very high quality, fairly well functioning company before the crisis hit. They have been restructuring themselves, but they certainly haven't been in danger of going bankrupt. So they have a bond. These are one-year bonds. So we're looking at cash flow 1, and we're assuming in this case we have these are annual pay bonds with just cash flow 1 coming up. And we have here the promised cash flow from this bond is again 100. And then again, our boss or our general manager, our CFO, has done a lot of work and estimated that GE might run into trouble with this bond. It might have to declare bankruptcy. And if it does, we estimate we will get something, right? Because bondholders typically get something in bankruptcy. And the CFO or our boss's best estimate is that would be $65. And we have some probability of worst case that we want to solve for. And we know that if we get the right answer, the expected value cash flow is 98.25. So let's see if we can set this one up. This is going to be exactly the same thing. So I'm going to start with x times, we need to solve for x, which is this over here. Okay, so I've got x times the probability of the worst case is associated with the 65, plus I have over here the 1 minus x times 100 is equal to 98.25. Okay. Okay, so I think if we do the algebra on this guy, we're going to find that x equal 5% works. Of course, I've already done the algebra, so let me just show you that that is really true here. So I'll bring this down here and I'll put in 5% here, and I'll put in 1 minus 5% here, and I'll turn this into an equation to be solved, and we have a little formatting issue there. And once we get that solved, we do see that 5% probability of worst case does give us our 98.25. So I'll just come back over here and say x equals 5% for that one. Okay, and then let's go ahead and see if we can do the same thing here with United Airlines. Now, United Airlines definitely is a company that is in grave danger of going bankrupt because of the coronavirus problem. They're estimating that they're going to have 6% capacity on their planes. Right now, they're running at about, as I create this lecture, they're running at about 25%. So clearly, given their fixed costs for paying their pilots for fuel, for maintenance on their planes, things like that, they're going to be wildly cash flow negative from their operations and go bankrupt very quickly if they don't get help from the government. So once again, our boss has thought about a lot of things. She has a view on what kind of bailout, if any, they're going to get, et cetera, et cetera. So she comes up with worst case if they do go bankrupt, that because they do have planes and things like that that can be auctioned off and sold to the sold for the bondholders to get the proceeds, that there will be something there. And she believes that there's a 75% probability that United Airlines and other good airlines are going to go bankrupt, and her expected value here is 70. So let's see if we can back into the promised cash flow in this case for United. Okay, so in this case, we're going to have her best case is only 25%. So we'll put that in equals 25% times x, and then plus 75% times 60 is equal to 70. All right, so in this case, we just solve for x. So we can say x is equal to 70 minus 75% times 60. And that whole thing needs to be divided by 25%. And that looks good to me. And we'll go ahead and solve that. Okay, and indeed we get 100. So in this case, x equals 100. So this was $100 promised for cash flow one, same as the other two. Okay, and so what have we done here? The nice thing about this table is that it tells us everything that we need to know about the project-specific risk for these bonds. We've explicitly considered the best and worst case cash flows, their probabilities, and the expected values. If we kept repeating this by the Treasury experiment in a situation like the height of the 2020 coronavirus outbreak, we'd get on average over the long haul 99.8 and et cetera, et cetera. Okay, good. Our framework for modeling financial risk and reward that we're going to use going forward when possible, especially for our cash flows, is like this. We're going to admit that our cash flows and our discount rates are random variables. We're going to estimate a probability distribution for these quantities, and we've pretty much just covered how we're going to cover cash flows for zero coupon bonds. And we'll use the expected value to estimate our future reward, and we'll use some measure of our distribution spread, standard deviation, or something like that to estimate future risks. So to do that and to generalize what we've done here beyond something like 1-year bonds where we're considering the cash flows as Bernoulli distributed, we need to go a little bit farther into thinking about statistics and probability. So let's consider cash flows versus returns and start with a 1 year 2 cash flow project where we have cash flow 0 and cash flow 1. Cash flow 0 is, as always, now, okay, and this is going to be in 1 year. So cash flow 1 is clearly a random variable. It's measuring the uncertainty of cash flow 1. We want to measure that uncertainty of cash flow 1 via a probability distribution. We also want to start thinking about returns for this project. And we define our return for a project like this as the cash flow that we get back at the end of the project, that's cash flow 1, minus the cash flow we put into the project at the beginning, that's cash flow 0, divided by the amount we put in the beginning. So since cash flow 1 is a random variable with a probability distribution, the return is also going to be a random variable with a probability distribution. So let's consider another 1 year project. Let's consider we buy a stock today, we hold for 1 year, and we sell at the end of 1 year. Or if we think we're going to continue to hold the stock beyond that, we will pretend that we're selling at the end of the year. Okay, so in this case, it's pretty easy to compute the return for this project. That's going to be the price of the stock at the end of the year. Okay, so this is at EOY 1, and this is minus the price at t equals 0, which is EOY 0, and divided by the price at end of year 0 when we start the project. Okay, and so going forward for the rest of this chapter, we're going to model our risk and reward with either cash flows or returns.